In section 3.10, we will explore related rates. So, when we're thinking about related rates, just remember that calculus is the study of change. So, of course, what is the one thing that everything changes with respect to? Well, that is time. So, if we're going to be looking at these problems, keep in mind that our variable that we're going to be differentiating with respect to is going to be t. So, we'll be looking at functions like dy over dt, where y is some differentiable function with respect to time, that is. So in our first example, suppose that we have a dimension x and the area A equals 7x squared of some shape. These are both differentiable functions of time t. We're asked to write an equation that relates the change in area to the change in the dimension with respect to time. So we have our given equation. This time A is equal to 7x squared. And if we want to go ahead and find the derivative, well, take the derivative of A. That is to say, we get dA dt. Now, the other side. 7 is a constant multiple, so we can just bring that along. And when we take the derivative of x squared, we get 2x. And of course, because x is not t, obviously, we just go ahead and take the derivative implicitly. That is to say, we get dx dt. Simplifying this a little bit, we have dA over dt is equal to 14 x dx dt. And again, this is what we were asked for. We have an equation that relates the change in area, that is to say dA over dt, to the change in the dimension, which is dx dt. And of course, the variable that we're working with, that we're taking the derivative with respect to, is t. In this next example, we're going to go ahead and assume that x is equal to x of t. That is to say, x is some function of t, and it doesn't really matter which it is. It depends on the model that we're looking at. For example, like x may equal like t squared, and then y is also a function of t. So it would be like t plus 1. And again, these are just examples. We're not given anything in particular, so we don't have to worry about it. Of course, if we were, we can go ahead and just do a quick substitution. So let's go ahead and erase that. So we just assume that x and y are two differentiable functions of t. And then we're given some information. That is to assume that we have a relationship given by the equation x is equal to y cubed minus y. We're also given that dy dt is equal to 5. And then we're asked, what is dx dt when y is equal to 2? So, of course, in our original equation right here, we do not have anything relating to dy dt or dx dt. But obviously, to get that, all we need to do is take the derivative implicitly with respect to time. So when I take the derivative of x, I get 1 dx dt. Then I take the derivative of y cubed, I get 3y squared, and then I multiply by dy dt because y is a variable, that's not t. And then again, when I take the derivative of y, I get 1, but then multiply it by dy dt. If I look at this, I have a lot of information given to me. For example, I am looking for dx dt, and that is right there. I also have y given to me. So here's my y is equal to 2. There's y in my equation. And then dy dt is equal to 5, and you can see dy dt appears twice, so it's really just a substitution from this point. That's to say, dx dt is equal to 3, and I'm given y is 2, so that would be 2 squared, times 5 minus 5. Simplifying this a little bit, we get 3 times 4, which would be 12 times 5 minus 5, and 60 minus 5 is 55. So down here below, we have another example involving a circle. Dx, or x squared plus y squared is equal to 25, and we're given that dx dt is equal to negative 2. And then we want to go ahead and figure out what is the change in y with respect to time when x is equal to 3 and y is equal to negative 4. I encourage you to pause the video and go ahead and give this a quick try. So here's the solution. So again, I'm going to just take the derivative implicitly. So that is going to give me 2x squared. Excuse me, not 2x squared, just 2x because of the power rule. And then we're going to take the derivative with respect to time. So we multiply by dx dt. Same thing with the y squared. We get 2y dy dt. And the derivative of 25 is 0. And you can go ahead and solve this for dy dt if you want, but what I think is easier just to go ahead and do the substitution and then just manipulate the numbers. So I'm given x is equal to 3, so I have 2 times 3, and then dx dt is equal to negative 2. And then I have 2, and then y was given to be negative 4. And dy dt is what I'm looking to solve for, so I'm going to just leave that as that variable. And that's equal to 0. So now just clean up from here. 2 times 3 is 6 times negative 2 is negative 12. And then this is going to be equal to a plus a negative 8 times dy dt. So going over here now to finish off the computation, I will add 12 to both sides. So I get negative 8 dy dt is equal to 12. And divided by negative 8, I find that dy dt is equal to 12 over negative 8, or 3 over 2 with negative. This example is very similar to the last one, except for some of the variables or the letters will actually just be assumed to be a constant. So at that point, they wouldn't really be a variable, but makes it easy when you take the derivative of a constant is just going to be 0. So you can see in this first example, we're asked to figure out how is ds dt related to dx dt if y is a constant. So you can see right here, we have our function. So let's go ahead and rewrite that in this spot for a. So that is to say s is equal to x squared, which is being treated as a variable because we're looking for dx dt. Then we're going to need to find the derivative of this function, and the rest of the function is the square root of 1 plus 2y. Now, here's the thing to be careful of. Notice that y is assumed to be a constant. So this whole expression right here is just going to be some constant. So that means when I take the derivative, I do not need to worry about the product rule or anything to that effect. So let's go ahead and take the derivative. The derivative of s with respect to t is just ds dt. The derivative of x squared is 2x times dx dt. And this whole expression in the square root is just a constant multiple because y is a constant. So we're just going to be multiplying that by 1 plus 2y. And there we have it. We have a relationship between ds dt and dx dt. That is to say that ds dt is equal to 2 times the rate that x is changing with respect to t times x times 1, or the square root of 1 plus 2y, where y is some constant. Again, we're not modeling anything in specifically, so we don't have any physical interpretation of that. So with that in mind, I would go ahead and encourage you to go ahead and think about the next ones. The next one's a little bit tricky because x nor y are assumed to be a constant. So that means you're going to have to use a product rule because this is the function, or this is the product of two functions. So go ahead and give that a try. Let's go ahead and look at the solution. So in order to find the solution, I just needed to take the derivative of this function s, which is equal to x squared times the square root of 1 plus 2y. So here we go. So taking the derivative of s with respect to t, nothing tricky there, just ds dt. Now I'm going to have to use the product rule. Again, do note that this right here is just equal to x squared times 1 plus 2y to the 1/2. So we are going to have to use the chain rule here. So first, which is x squared, times the derivative of the second. So I'm going to go ahead and take the derivative of 1 plus 2y to the 1/2. That would be 1/2. And then I have 1 plus 2y to the minus 1/2. And then I have to take the derivative of the inside. The derivative of the inside is just going to be 2, and then we're going to have to multiply the derivative of 2y is 2 dy dt. And then we have the rest of the product rules. So x squared plus the derivative of the second, and then the second, which is just going to be the square root of 1 plus 2y times the derivative of 2x squared, which would be 2x dx dt. We could do a little bit of cleanup here. So that would be, we'd have x squared on the top, and then we'd have 2 times the square root of 1 plus 2y. And then we also have a 2 from right here. And then we also just are multiplying by dy dt. Then cleaning up the second half, typically we're going to write our constants times our variable x, and then we'll have the radical 1 plus 2y multiplied by dx dt. All right, and then the last one, very similar to the first one, except for we are going to treat s as a constant. So when we're treating s as a constant, let's rewrite our function. S would be equal to x squared plus, not x squared plus, but x squared times 1 plus 2y. And when I take the derivative here, well, ds dt is not needed this time because s is assumed to be a constant. And well, we already took the derivative of this product in the example above. So we find that it is equal to 2x squared over 2 times the square root of 1 plus 2y times dy dt plus 2x times the square root of 1 plus 2y dx dt. And then how is dx dt related to dy dt? Well, we just need to go ahead and solve for one of them. And when you do this, I'm going to go ahead and take this second term right over here, and I'm going to subtract that from both sides. So that is going to give me minus 2x times the square root of 1 plus 2y times dx dt equal to the 2x squared over 2 square root of 1 plus 2y dy dt. Then you're just going to go ahead and divide both sides by this minus 2x square root of 1 plus 2y. And then when I do that, I'm going to go ahead and write the answer over here. So what this would turn out to be is dx dt is equal to, let's see, we're going to have some cancellation because this expression right here is going to be on the bottom if you're thinking about the multiplying by the reciprocal. So forgot to write that there. So we have 1 plus 2y. So we're going to have a negative. The 2's are going to cancel, and 1x is going to cancel. We're going to be left with an x there in the numerator. So that 2 canceled, that 2 canceled. The square cancels with that x. The negative is still going to be there. We're going to have a 2 in the denominator still. So this 2 will just come along right here. And then you have the square root of 1 plus 2y times the square root of 1 plus 2y. So that is just going to be leaving me with 1 plus 2y. And of course, dy dt. So there is our expression relating dx dt to dy dt if s is held to be a constant. In the previous examples, it was very easy to see what we were looking at with respect to time. So for example, we were given very explicitly that ds over dt was a constant, or we had that dx over dt was equal to 2 or something like that. I can't remember. But when we're using this idea to model certain situations, for example, heating a plate, don't burn yourself. So let's consider this situation. When a circular plate of metal is heated in an oven, its radius increases at a rate. Ooh, keyword rate means that this is probably going to be d something with respect to time. And if we look at this right here, this 0.01 centimeters per minute is definitely going to be with respect to time. And, well, let's think about d something with respect to time. And if we're looking at the rest of this problem, at what rate is the plate's area increasing when the radius is is 44 centimeters? Well, definitely now we can see that that rate that we were talking about increasing earlier is simply r. So we're given that is just to be 0.01. And again, just to keep track of our units, that's centimeters per minute. And we were asked at what rate is the plate's area increasing. So that is to say, we're just reading through this and collecting some information. We were asked to find the change in area with respect to time when the radius is 44 centimeters. That is to say, not time, but the radius is given to be 44 centimeters. And our units match, so that's good to keep in mind. Notice there's nothing given about a formula here. So this does require some background knowledge, and of course, if we're talking about something that is circular, we have a formula in mind, that is to be pi r squared. And just take the derivative of this with respect to time. The derivative of a with respect to time is dA dt. Pi is a constant, so that's just going to be pi times 2r. And then, of course, r is not t, so we're going to multiply by dr dt. And you can see we now have an equation with basically everything we need except for this. Oh, we're asked to find that, so that works out fine. In other words, dA dt is equal to pi times 2 times r, and that was at 44. And then we're going to multiply that by 0.01 centimeters. And then again, this is technically, again, this centimeters. And then area would be squared, and we can see our units 44 SCM, the dr dt has cm per minute. So when we're asked or given some information, we do need to go ahead and think about, well, do I have a formula relating that information? So in example 5, we are asked to consider the changing dimensions in a rectangle. So keep in mind we have several formula related to a rectangle. So suppose that we're given edge lengths x, y, and z. So length times width times height, you can think of it as we're just encoding that information in x, y, and z instead. And we have a closed rectangular box, and the edge lengths are changing at the following rates. The change in x with respect to time is 2 meters per second, so it's growing. Dy dt, so if you're thinking length times width, the width is shrinking, so dy dt is negative, 2 in this case. And dz dt is equal to 1 meters per second, so it's also growing. So no need to worry about getting squished. Good. Now, we're asked to go ahead and find the rate in centimeters, and well, let's go ahead and simplify things a little bit. Let's just go ahead and turn this into meters so we don't have to worry about changing units, and we can just focus on the calculus. At which of the boxes, let's start over. Find the rate in meters at which the box's surface area is changing at the instant when we have x is equal to y, x is equal to 4, y is equal to 3, and z is equal to 2. So again, what formula am I going to need? I'm going to need something about the surface area of a box. So again, let's just go ahead and call it area for short, and we're in 3 dimensions, so that's why we're talking about the surface area. So if we're thinking about the surface area of a box, well, we need a formula for it. So again, if you don't remember it, that's fine. Just realize you could think through this. So let's go ahead and get a rectangular box. And I guess this is a square, so don't assume that it is square. So be careful with that when you're doing any sort of models. So let's see. We have the bottom and the tops. So let's go ahead and assume this is our length is 6. We have y, and then we have z. So if we're looking at each of the faces of the box, well, the bottom of the box is going to just be x times y, and we have 2 of those. So we have 2 times x plus y. And then the side of the box, we have 2 copies of y times z. And then the last one, let's see, we've done the bottom, the side, and now let's do the front. So we have 2 copies of x times z. And now let's go ahead and pet my cat. I don't know if you could hear that in the video, but she wants attention and I want to do math, but that's beside the point. Anyway, so we need to go ahead and find the rate at which the box's surface area is changing. So in other words, we need dA and dt. Well, then the rest of this is just going to be taking the product rule a few times. You can factor out the 2 to keep it simpler, so we're going to have 2 in front. So that is to say we can think of original as xy plus yz plus xz, and just using the product rule a few times. So let's see, we have x times dy dt plus y times dx dt. So that first derivative was taken care of. So now let's go ahead and do the second derivative. So that is to say we have y dz dt plus z dy dt. And then lastly, we have xz. So that would be x dz dt plus z dx dt. So now we have all of the information that was given. So we have 2 times, well, x was just given to be 4. dy dt was given to be -2. Then we have plus, this 2, I'm going to just have it affect everything. So we have that first one, then we have y, which was 3, and then we have, let's see, y, then dx, dt, a little typo there. So dx dt was given to be 2. And then we have, I'll switch to red just so we can keep track of everything. Y was 3. Then dz dt was 1. And then plus z, which is 2. And then we're multiplying that by dy dt, which is -2. And then we have x, so x is 4, times dz dt is 1, plus z, which is this case 2, times dx dt, which was also 2. All right, and we're almost done. So we have 2, and then this is -8 plus 6 plus 3 minus 4 plus 4 plus 4, and then, well, here we go. So this 4 cancels with that, and then we have 6 and 4 gives -4 gives me 2, so that's going to give me 2 times 5, which is equal to 10. So it is definitely a good thing the surface area of this box is increasing, otherwise we would get squished. As you have seen, there is a general problem-solving strategy that does rely on interpreting that information. So the first thing you'll want to always make sure you do is just read the problem, and if you're not understanding it, draw a picture and just make sure you understand all the variables and constants. And of course, everything's changing with respect to time and related rates, and it is safe to assume that all variables are differentiable functions of t. So hence we've been taking like dx dt, dy dt, dr dt, etc. Of course, write down what you're given and write down what you're asked to go ahead and find. Because honestly, once you know what you're looking for and what you're given, it's not too hard. Assuming that you do have an equation for the relating the variables, and here is our few examples below. Just as you work through, you'll get comfortable with the different formulae, whatever. And of course, 5, differentiate. That's pretty straightforward at this point. And of course, evaluate to find the unknown rate. As you have probably started to see, some of these can get a little bit tricky, but again, just keep in mind to draw a picture, figure out what you're given, figure out what you're asked to go ahead and find, differentiate, and then plug in. So it's really not hard, but it does take some very patient reading of what you're given. So let's go ahead and look at a few harder examples together. Of course, I would encourage you to really just sit down and try these first on your own, but here's a solution. So water is running into a conical tank at a rate of 9 feet cubed per minute. So that is to say, I have a tank that is going to be conical. So let's go ahead and just consider something that's cone-shaped. So let's get a cone. I'm not the best artist, but hey, it gives me what I need. And then water is running into this right here. So, and again, what is that running into? And if you look at the units, it's giving you a hint of what this actually is. Feet cubed. So that's probably actually going to be the change in the volume since we're a cube. So dV dt, and again, the rate was the hint that this is respect to time. So that is to say, it's just simply going to be 9 for the numerical part, which is important, and of course, feet cubed per minute. The tank stands point down, and of course, I already drew that like that. I had read this problem beforehand. And has a height of 10 feet. Okay, so that's good to know. So that height of this cone is going to be 10 feet. So notice that's not a rate. It was a variable given to me. And it also has a base radius. Of course, the base of the cone right here is going to be, so if we can think right here, this is the base radius. So a little hard to see, but that is just going to be 5 feet. So R is equal to 5. How fast is the water level rising when the water is 6 feet deep? So we're asked, how is it rising? So if we're thinking about the water level, was the max it could be is 10 feet. And, well, that is to say we're looking for dH dt. How much water height is it rising? So, and when the water is actually 6 feet deep. So this is going to give us the height of the whole tank. But careful, what we're really looking for, and I could have the notation match this, is we're looking for dH dt when the height is given to be 6 feet. So this is really what we're looking for. So we do need a formula relating all of this information. And the volume for a cone is equal to 1/3 pi r squared h. Am I given this information? Okay, yeah, I'm given a rate of change for v. I'm given a radius, which is right here. I'm given a height, which I need 6. So be careful with this 10. That was a little bit of a distractor, but it's just telling us kind of some constraints on the height that we're going to be looking like. So for example, it wouldn't make sense to ask for the change in height when the height is equal to 11 because it's overflowing, and well, that's just a mess. All right, so let's go ahead and differentiate. Oh, wait. We have a bunch of variables here. We have v. Okay, that's fine because we're given that when we differentiate, that'll be dV dt. But we have an R and we have an H. And if you're thinking about that, R is going to be smaller whenever we're inside the looking at the water level of the cone. So it's not held constant. So what we need to do is figure out some relationship between R and H, and we want everything in terms of the in terms of H, because that's what we're going to be looking for. We need H equal, or we'll be able to plug in H equals 6. So how are we going to go about doing that? Well, let's think about what is the relationship between the height and the radius of this object. And honestly, this is where it gets a little bit tricky. So if we're looking at this, we are given a height of 10 and a radius is 5. What we need to go ahead and figure out is this height and this radius. And what we really have is a case of similar triangles. So this right here is 10, the top was 5. So what we're going to find is that the ratio is the height to the base is equal to R, that would be H over R. And now if we go ahead and just solve this for R, we would simply just cross multiply and get 10R is equal to 5H, and then dividing by 10, we get R is equal to 5H over 10, or R is equal to H over 2. So now what we can go ahead and do is plug this back in, and we have everything in terms of the two variables that we know. So let's go ahead and finish that off. So let's see, we would have v is equal to 1/3 times pi, and then r is equal to h over 2 squared, and then we have our original h. So v is equal to 1/3. We're going to have pi h cubed over 4. All right, now let's do one more step of cleanup. 1/3 so times 1/4 is going to give you 12. So let's just go ahead and what do we have on top? We have pi h cubed on top, 12 on the bottom. Differentiating with respect to time, we find dv dt is equal to pi over 12 times 3h squared. Taking the derivative with respect to time, we tack on dh dt. And now it's just a matter of plugging everything in. So we were given dv dt is equal to 9. We can go ahead and do some canceling on the right. For example, 3 divided by 12 is just going to give me a pi over 4. When I plug in 6 for h, I'll just do that in the next step, 6 squared, and we have dh dt. So that gives me 9 is equal to, well, 6 squared is 36. 36 divided by 4 is 9. So 9 pi times dh dt. Well, that works out really nice. So that is to say that dh dt is just going to be 1 over pi. So again, this example was a little bit harder, but it does give us an idea of the power of related rates and just in allowing us to get information about different models.